Suppose that you were trying to get a robot to go somewhere. You could try to talk to the robot and try to tell it, for example, to go to Los Angeles, New York, or that boring English class that you're taking. But the robot doesn't know how to do that. Just like a 1-month-old baby, it doesn't know how to walk, nor does it know where it currently is. In the end, you're just leaving it confused as to what it's supposed to do. This is where control theory comes in. The field of control theory focuses on defining functions that dictates how something should operate or move. It's like giving an artificial brain to a robot. With the knowledge of control theory, you can, for example, control robots. AI in games also utilizes methods proposed in this field, and often borrows ideas from robotic control to get characters to do what we want. Also, in a way, you could say that living organisms have a form of control systems embedded in their bodies. Our brains are capable of locomotion, decision-making, and conducting various tasks like washing dishes, picking up objects, and so on. But before we dive deeper into this topic, let us go through some key terminologies. The robot's body or hardware and its surrounding landscapes, objects, etc. are called environment. The environment outputs information containing its features, like the position of the robot, what the robot sees in its eyes, or the angle and angular velocity of each of its joints. This is called state. The state of the environment becomes the input of the agent, or the brain of the robot. The agent then decides what to do next, given the information about the environment, such as the torque or force on each of the joints, or in other words, selects the action given the state. Given the action, the state of the environment changes accordingly. The simplest control system framework is called open-loop system. The agent merely takes the initial environment state and figures out the sequence of actions that completes a task. But as you can probably see, it can get a bit unstable, since the agent cannot take the consequences of its actions onto the environment state into consideration. It's almost like looking at a street that you've never been to before, closing your eyes, and trying to navigate through it, except the agent most likely doesn't even understand the concept of objects or location, so it just becomes a mess. Closed-loop systems solve this problem by adding a feedback loop that updates the environment state every time the agent outputs an action. This lets the robot know the effect its action have on its environment and act accordingly. Reinforcement learning is one example and field of closed-loop systems, and as you can tell by the title, will take up the majority of the video. Reinforcement learning is an algorithm that attempts to perform a specific task that is defined by something called the reward function. Let's look at an example. Say that you want a robot to go forward. The reward function defines how well it performed the task of moving forward. So in this case, it'll be something like the forward velocity, the forward position, or the forward acceleration. In addition to the mutual interaction between the agent and the environment with state and action, the reward is added onto the set of outputs of the environment. This means that for every action that the agent takes, the environment outputs the state and the reward. In the context of reinforcement learning, we will also refer to the agent as policy from here on out. Now that we have the overall understanding of the feedback loop within reinforcement learning, let's look at the individual parts that makes up this loop. When the environment updates its state, it takes the current state and the actions outputted by the policy into consideration. From the perspective of probability and statistics, the probability of the next state is determined given the probability of the current state and action. This probability distribution function is called the state transition function. reward function is also determined by the current state and action, but keep in mind that this is not a probability distribution function, and instead outputs the actual value of the reward rather than its probability. The policy, on the other hand, outputs the probability distribution of the action given the current state. The main goal of reinforcement learning is to find a function for the policy that chooses the action that maximizes the reward or its accumulative sum. Or in other words, we want the probability of the action that maximizes the reward to be high. Let's put this network of probabilities into a visual representation. The probability of the action is determined by the current state by the policy, and the probability of the next state is determined by the current state, and the current action by the state transition function. And of course, how could we forget, the value of the reward is determined by the current state and action. This type of visual representation is called the graphical model. You can apply this to arbitrary time steps from 0 to infinity. This type of decision-making process that is dictated by stochastic policies and environments are called Markov decision process. We now attempt to look at the mutual interaction between the agent and the environment through the lens of adversarial games, where multiple players that have their own agenda or reward function which can affect each other's performance. Adversarial games can be classified into cooperative games, where their interaction helps maximize each other's rewards, or competitive games, where each of the players' rewards play against during their interaction. Here we will be focusing on competitive games. Suppose we are simulating a competitive game with 2 players, and each player is able to choose from 2 actions. We first have an initial global state of S0. Player 1 can select from 2 actions. If player 1 selects the first action, the global state transitions from S0 to S10. If player 1 selects the second action, the global state transitions from S0 to S11. Player 2 can also select from 2 actions. The current global state does not affect this fact. The player can select from the same actions in either of the possibilities. The global state transitions according to the current state and the action selected by the second player. After enough time steps are taken, the global state reaches its terminal state, which determines the cumulative reward, otherwise known as terminal utility or return. Each player attempts to set the return to a certain value depending on their own set agenda or task. The simplest type of adversarial game is the minimax game, where player 1, the maximizer, tries to maximize the return, and player 2, the minimizer, tries to minimize the return. Let's set the terminal reward to a certain value, each being 15, 10, 7, and 18. Since the minimizer always chooses the state with the smallest expected return, we can conclude that the expected return of the previous state, S10 and S11, are respectively 10 and 7. On the other hand, since the maximizer always chooses the state with the maximum expected return, the expected return for S0 is 10. This process of determining the reward of previous states from the return is called pruning. Let us take this a step further. In expected max games, player 2, the minimizer, chooses its action stochastically or probabilistically. Player 2 still tries to minimize its return, but there is a certain chance that the action that induces the smallest expected return is not chosen. If we go back to the pruning process, we can see that the chance of selecting each of the actions by the stochastic minimizer is depicted with fractions or in probability. In this example, the chance of the player selecting the action with the smallest return is 2/3. while the chance of selecting otherwise is 1/3. By multiplying the return with the respective probabilities and adding them, we can calculate the return for the previous states. In this example, they are 11.7 and 10.6. The maximizer still chooses its action deterministically, so the expected return for S0 is still 11.7. The mutual interaction between the policy and the environment in reinforcement learning is similar to that of the mutual interaction between the maximizer and the stochastic minimizer in expect-a-max. Except, of course, we usually don't know the probability of the state transition function of the environment and the expected return for each state right from the get-go. In order to calculate the expected values of these variables, we conduct the trajectory sampling, where we run the policy, obtain the set of states and actions, and obtain the reward for that trajectory. From there, we calculate the state action value, or otherwise known as the Q value. We can also calculate the state value by taking the maximum value of the Q values for all combinations of states and actions. Considering everything that we have discussed here, from Markov decision processes to adversarial games, what does the agent in reinforcement learning consist of? Well, it consists of two things. The state action value function estimates the return of each combination of states and values by sampling trajectories. The policy references the values function and selects the best action. We can define each of these functions using deep neural networks. The synaptic weights of the neural networks are usually updated using the well-known optimization algorithm, gradient descent, which, as you may already know, takes the partial differentiation of the loss function by the synaptic weights. And this enables each of the neural network to maximize its accuracy. These types of reinforcement learning algorithms are called deep reinforcement learning. Let's quickly look at some examples of reinforcement learning algorithms. These architectures are determined by the type of function that you use to define the policy and value function. Monte Carlo method defines the policy as the argument maximum that references the Q table that contains the expected return for all combinations of actions and states. Sarsa updates the Q value via the Bellman equation, which defines the new estimate of return by adding the current reward onto the estimate of return, given the action and state of the next time step in the sample trajectory. Q-learning improves upon this by sampling the action of the next time step from an arbitrary policy, making this an off-policy algorithm. Entering the realm of deep reinforcement learning, we have deep Q-learning, which replaces the Q table with a deep neural network, reinforce, which uses the Q table for the value estimation but uses a deep neural network for depicting the policy, and actor-critic algorithm, which uses deep neural networks for both the policy, actor, and the value function, critic. Out of all the reinforcement learning algorithms that we have seen, we will focus on one type called policy gradient algorithms. Policy gradient algorithms refer to deep reinforcement learning algorithms where the policies are defined by deep neural networks and are updated via gradient descent. Some examples include reinforce and actor-critic, which we have seen before, and proximal policy optimization, and more recently, soft actor-critic. All policy gradient algorithms are based on a foundation called the policy gradient theorem. Let us first define an objective function that we want to maximize, which is just the definition of reinforcement learning in general. Finding a policy that maximizes the expected return. This is the sum of return per trajectory weighted with the probability of the policy following that trajectory. With the sum of infinite trajectories, This equation can be translated to an integral. Let's take the gradient of this objective function by the weights, theta, of the policy's neural network. If we multiply this by the fraction of policy over policy, which is equivalent to 1, we get the form nabla theta pi theta of tau over pi theta of tau. If you remember your calculus, the derivative of a logarithmic equation is equivalent to the derivative of its content over its content. Now we can see that we have effectively expressed the gradient of the objective function with merely the gradient of log policy and reward of the trajectory. Looking at the result, we can see where the policy and value function, or rather the actor and critic, come into play. But since we are sampling multiple trajectories with large variety from one policy, there is going to be a large variance in the estimated return by the state action value function, which becomes a problem when you're trying to update the policy based on an unstable value function. In order to reduce the variance, a certain baseline value is subtracted from the expected return, hence variance reduction. The most commonly used variance reduction technique is the advantage function, where you subtract the estimated return given the state from the estimated return given both the state and the action. This gives the relative effect the selected action has on the return of the trajectory. Here, we will be taking a look at one instance of policy grading algorithms called Proximal Policy Optimization. Proximal Policy Optimization is often used as baseline for testing reinforcement learning experiments. One defining feature of Proximal Policy Optimization is that it limits the gradient step it takes during policy optimization to a certain amount, which is dictated by the advantage function. Another important thing to note is that this is an on-policy learning algorithm, which means that the learning process relies on trajectories generated by current policy that we are trying to update. We have to throw away the trajectories that we have in our memory at hand every time we update the policy. Let's take a look at the algorithm as a whole. We can see that we are collecting trajectories generated from a particular policy, taking segments from the trajectory, and computing their returns. Then we use the return to compute the advantage function. The objective function contains a minimization function that acts as a clip or a limitation to the gradient step, pi theta over pi theta k, or the hyperparameter epsilon. The value function is computed by computing the least mean squares via gradient descent. And now we will look at the same code that I wrote around a year ago with my mentor at the time. We used the PyTorch reinforcement learning framework called RLKit. So this is the README page of our implementation of Proximal Policy Optimization using the framework RLKit. And if we click on the example script here, we can jump to ppo.py. Since we are using the PyTorch library, we have to first define a class that represents the policy and the value function. And those are represented using the flatten MLP class and the tanh Gaussian policy class. Let's look at the tanh Gaussian policy class. So here we can see that there is a forward function defined within the class, a predefined function within PyTorch where you can define the layers of the neural network. And in this case, we are using the hyperbolic tangent function as the activation function of each neural layer. If we look at the getAction and getActions function, we see that there is something called a return logprob or logprobs variable that is defined here. If we recall the loss function of Proximal Policy Optimization, we notice that we have to sample the log prob, or the logarithm of the policy, from the sampled trajectory. So we have to get the action and the log prob from the sample trajectory. If we go back to the ppo.py, we see another class defined here called ppo-mdp path collector. If we look at the definition here, we can see that this function defines what kind of variables to sample from the sample trajectory. And in this case, we see that this function collects observation, action, reward, next observation, the terminal, the agent infos, the environment infos, the advantage function, and the return function. Later on, we will see that the log probability of the policy are stored in the agent infos variable. If we take a look at here, we see that PPO environment replay buffer class is defined here. And this class defines the data extraction process from the sample trajectory. And if we see here, we see that the log probability is stored into the agent info, as we have seen before. We also see that there is a random batch function defined here, which generates a random integer which represents the index of the arrays. And this enables us to extract a sample data that represents one time step from the batch of the sample trajectory. The most important class in this entire program is probably the PPO trainer. And if we take a look at the PPO trainer, we see that this class defines the loss function for Proximal Policy Optimization. If we take a look at the function train from torch, we see that here we see the actual loss function of the Proximal Policy Optimization, defined by the advantage and the hyperparameter epsilon. We also see the loss function for the value functions. Finally, let's take a look at PPO torch batch RL algorithm class. This class, or underscore train function in particular, defines the overall process of sampling a trajectory, sampling a data from that batch, and training the policy and the value function. So for every epoch, or every time you update the function, you sample a trajectory and add it to the replay buffer variable. And from the replay buffer variable, we sample a random training data, and we use the training data to actually train the policy and the value function. This is a footage of the PPO in action on a bipedal walker environment. And with that, we conclude our overview of reinforcement learning. Thank you.